Hello and welcome back to our deep dive. We are going to jump straight in today with a scenario from the chemistry lab. It's a classic puzzle, really.
One of those things that looks simple on the surface, but
Mm.
and hides a lot of complexity. I'm always ready for a good puzzle.
Okay, so picture this. You're in the lab, you have two test tubes, and first you've got some ethanol, just plain old alcohol.
Right.
And the second one, you have diethyl ether. Now, they look identical, don't they? Both are clear, colorless liquids, and chemically, they're basically cousins. Carbon, hydrogen, oxygen in both.
They're actually isomers in this case. Same formula, just a different arrangement of atoms.
Exactly. So you take a dropper of acidified potassium dichromate, that bright orange stuff everyone knows,
It's a classic oxidizing agent. Yes.
and you add it to both tubes. Now, in the ethanol tube, you get instant drama. The orange solution flashes to green.
A clear reaction. Oxidation is happening.
But then you look at the second tube, the
Yeah.
one with diethyl ether,
Yeah.
nothing. Absolutely nothing happens. The orange color just stays orange.
It completely ignores the region.
So that's our question for today. Why? They have the same ingredients. They both have oxygen. Why does one react so dramatically while the other one just sits there like a stone?
To answer that, we have to look beyond the formula. We need to look at the architecture. Today we're diving into Unit 7, alcohols, phenols, and ethers. And our goal isn't just to list reactions. It is to understand the structures of functional groups.
And that's really the power tool for organic chemistry, isn't it? If you get the structure, you don't have to memorize thousands of reactions for the board exams.
That's the entire point. Memorization can fail under pressure. But if you understand the structure, you can actually predict how a molecule will behave. You can look at something new and make a very educated guess.
So let's strip this down. What's the fundamental rule here? What's the simplest way to think about it?
At the simplest level, the rule is this. A functional group's chemical personality is determined by its immediate environment, especially the bonding environment of that oxygen atom.
I like that word personality. It suggests the oxygen atom itself changes based on its neighbors.
Precisely. I want you to imagine the oxygen atom as a single red Lego brick. It's the same brick every single time.
Okay.
But where you click it into the larger model completely changes its function.
Right. So let's walk through our three cases: alcohols, phenols, and ethers. Where does the Lego brick go?
Okay, case 1. You click that oxygen brick onto a simple saturated carbon chain. A straight line of blocks.
Like in ethanol.
Exactly. In that position, it behaves as an alcohol. It's reactive, it's flexible.
Okay. And case two?
Case 2, you take that same oxygen brick, but you click it onto a benzene ring, that flat hexagonal structure,
Ah, the aromatic system.
and suddenly it behaves as a phenol. It becomes acidic. Its entire personality changes.
And the third one? The ether.
For the ether, you use that oxygen brick as a bridge. You click it in between two carbon chains. It's holding hands with a carbon on its left and another on its right.
So COC.
Yes. And now it behaves as an ether. It becomes, well, almost completely inert, unreactive.
It's the same atom, but location is destiny.
Structure is destiny. That's the takeaway.
Now, Legos are a great start, but for the exams, we need the technical details. Let's zoom in. What's actually happening at the particle level? Let's start with alcohol.
Okay, in an alcohol, that oxygen is attached to a carbon that is hybridized.
Spapapapa. So in simple terms, that's a tetrahedral shape, right? Like a pyramid.
Correct. The bond angles are around 109.5 degrees. It's a very spacious, comfortable arrangement. The bond between the carbon and oxygen is a straightforward single bond.
And critically, that oxygen is holding onto a hydrogen.
Yes. And that OH group is key. It makes the molecule polar and ready for hydrogen bonding. It's like it's waving at other molecules ready to interact.
Okay, so alcohol is spa, tetrahedral, and very social. Now, what about phenol? You said the benzene ring changes everything.
Drastically. In a phenol, the oxygen is attached to a carbon that is spot hybridized.
Which means it's part of a flat planar system.
Exactly. And that carbon is part of the benzene ring's conjugated system. The ring is like a circuit of electrons.
Right.
And the oxygen's lone pair of electrons get pulled into that circuit. This is resonance.
So the ring is borrowing electrons from the oxygen.
Yes. And this does two crucial things. First, the CO bond gets a partial double bond character. It becomes stronger and shorter.
Which is why it's so much harder to break in substitution reactions compared to an alcohol.
Precisely. And second, since the oxygen is sharing its electrons with the ring, the hydrogen attached to it becomes, well, much easier to remove.
It becomes more acidic.
That is why phenols are acidic. The ring helps stabilize the negative charge after the proton leaves.
Okay, that's a huge distinction. Now, what about the third one, the ether, the one that did nothing in our experiment?
In an ether, you have that COC structure. The oxygen is sitting between two carbons. The geometry around the oxygen is still bent, like in water, around 110 degrees.
So if it's bent like water, why is it so chemically boring, so inert?
It all comes down to exposure. The oxygen has two lone pairs of electrons. In an alcohol, they're sticking out. In an ether, those lone pairs are basically sandwiched between two bulky carbon groups.
So they're physically blocked.
Exactly. We call it steric hindrance. The alkyl groups act like bodyguards, preventing other reagents from getting close to the oxygen. The reactive part is buried.
And that's why the potassium dichromate couldn't react. It literally couldn't get to the oxygen.
That, and there's no hydrogen on the oxygen to remove. Oxidation often involves removing an H from the O or the adjacent C. Ether has neither in an accessible way.
I think this is where students get trapped. They see the letter O in a formula and they just assume the chemistry will be similar.
It's the biggest mistake trigger. Seeing of H or O and thinking they are the same.
And the fix is?
The fix is to stop looking at the oxygen in isolation. Look at its neighbor. Is it a saturated carbon, an aromatic ring, or is it another carbon? The neighbor defines the personality.
Okay, let's try another way to picture this. An analogy. Let's imagine the CO bond is a bridge over a river. How would our three structures look?
I like that. A bridge analogy. Let's build it.
So an alcohol. I'm picturing a simple wooden footbridge in a field. It's open, it's accessible, you can easily get to it to cross it or to break it.
That fits perfectly. It's reactive. The CO bond is accessible. It's a standard functional bridge.
Now, a phenol, this isn't a footbridge. This is more like a drawbridge attached to a huge stone castle. The benzene ring is the castle.
And the castle reinforces the bridge.
Yes. It has these massive support beams running from the castle walls to the bridge. That's the resonance. You can't just come and chop this bridge down. It's part of the fortress.
And that explains the partial double bond character. It's much stronger. You need a siege to break that bond.
Finally, the ether. This is like a bridge, but it's completely enclosed inside a tunnel. The two big carbon groups are the thick concrete walls of the tunnel.
The connection points are buried deep inside.
Right, it's protected. You can throw things at the tunnel all day, but the bridge inside is totally safe. The reagents just bounce off the walls.
A perfect description for why ethers are so inert. They are sterically shielded.
And why do we need these analogies? Why is this so important?
Because without it, you can't solve the problem of prediction. You can't explain why phenol is acidic with a pKi of 10, but ethanol is neutral with the pKi of 16. It's not random. The structure provides the reason.
It provides the logic.
Exactly.
Let's try one more visualization, a mental movie. If you're listening and can do so safely, just close your eyes for a moment.
Let's set the scene.
Scene 1. Alcohol. You're looking at a central carbon atom. It has 4 arms in that tetrahedral shape. One arm holds an XOH group. Zoom in on that oxygen. You can see its lone pair electrons pointing outwards, waving. They look available, ready to react. Label this image, open, reactive.
Now, shift to scene 2. Phenol. You see a flat, stable hexagon, the benzene ring. There's a current of electrons flowing around it, and that current flows up into the oxygen atom. The oxygen is glowing, let's say a faint purple. With this shared energy, it looks reinforced. Label this, resonance reinforced.
And scene 3, ether. You see an oxygen atom literally sandwiched between 2 big carbon spheres. The oxygen's lone pairs aren't waving, they are pointing inward. Tucked away between the carbons, it looks sealed, protected. Label this, sealed, inert.
If you can remember those 3 images, open, reinforced, and sealed, you have the core concept of this entire unit.
So let's apply that sealed concept. Being unreactive sounds boring, but in a lab, it can be a superpower, can't it?
It is absolutely essential. That's where solvents come in.
Right. Let's talk about THF tetrahydrofuran. It's an ether, and it's used for Grignard reactions.
Yes. Now, Grignard reagents are extremely powerful, but also extremely unstable. They are very, very reactive. They'll attack any acidic hydrogen they can find.
So if you try to do a Grignard reaction in ethanol,
it would be a complete disaster. Remember the open reactive alcohol? The Grignard reagent would immediately attack the hydrogen on the OH group.
And your reaction would be ruined before it even started.
Instantly. You'd just be destroying your expensive reagent.
So why is THF, the ether, the perfect choice?
Because it's the sealed structure. It's polar enough to dissolve everything, but it has no acidic hydrogen. And its lone pairs are tucked away. It acts as a neutral host. It provides the environment, but doesn't interfere.
It's like a good waiter at a party. It serves the drinks, but doesn't get involved in the conversation.
That's an excellent way to put it.
Now, one more tricky point before we recap for the exams. It's a bit counterintuitive. Do ethers hydrogen bond at all?
This is a very good question, and it's where the top marks are won. You might think oxygen is present, so hydrogen bonding must happen.
It seems logical.
But you need two parts for a hydrogen bond, a donor and an acceptor. A donor is a hydrogen attached to an electronegative atom like oxygen. Ethers do have an oxygen with lone pairs, so they can accept a hydrogen bond. If you put an ether in water, the water molecules can bond to the ether's oxygen.
So they can be a receiver.
But they cannot donate a hydrogen bond. Look at the COC structure. There is no hydrogen attached to the oxygen.
The cupboard is bare.
Exactly. They can't form hydrogen bonds with each other. And this is why ethers have much lower boiling points than alcohols of similar mass. They don't stick together as strongly.
That makes perfect sense. Okay, I think we are ready for a rapid-fire round of exam-safe clarity lines, the key sentences for getting full marks.
Let's do it.
First up, hybridization. What's the key difference?
You should write, the carbon atom in an alcohol's COH bond is spool hybridized and tetrahedral. In a phenol, the carbon is spool hybridized and planar.
Next, why is the bond in phenol stronger?
The key phrase is partial double bond character. The sentence is, due to resonance, the CO bond in phenol acquires partial double bond character, making it stronger than the pure single bond in alcohols.
Perfect. Acidity, the core reason.
Focus on stability. Right. Phenol is acidic because the resulting phenoxide ion is resonance stabilized. The alkoxide ion from an alcohol has no such stabilization.
Okay. The bond angle in an ether.
Be specific. The COC bond angle in ethers is approximately 110 degrees, slightly larger than the tetrahedral angle due to repulsion between the alkyl groups.
And finally, a summary of why ethers are inert.
Right. Ethers are chemically inert due to steric hindrance, which makes the oxygen lone pairs inaccessible and the absence of an acidic hydrogen atom.
Fantastic. Those 5 points are crucial.
Absolutely.
Okay, let's bring this deep dive home. To summarize everything for revision, what are the key takeaways?
First, remember the Lego principle. The same oxygen brick behaves differently, reactive, acidic, or inert depending on where you connect it.
Second, the mental movie. Alcohol is open and waving, phenol is reinforced and glowing, and ether is sandwiched and sealed.
And third, the solvent example.
Yeah.
We use ethers like THF for Grignard reagents precisely because their sealed structure is inert and doesn't interfere.
Which leaves us with a final thought for you, the listener. We've seen how just changing the carbon neighbor from spit to sp can completely alter a molecule's personality.
It really makes you think about the sensitivity of biological systems.
Exactly. Our bodies are built from these very functional groups. If a tiny structural change can turn a neutral alcohol into an acidic phenol, what does that imply about a single mutation in our DNA?
It implies that a tiny change in structure could turn a vital enzyme or hormone into something useless or even harmful. Life operates on this incredibly precise structural engineering.
Structure isn't just a topic for an exam, it's the fundamental code that keeps the entire machine of life running.
It certainly is.
Thank you for decoding some of that with us today.
It was my pleasure.
And to all of you listening, keep visualizing those molecules. Happy learning.